You can recall that in our previous two videos, we considered the volume of solids of revolution. In both cases, we were revolving a rectangle that was perpendicular to the axis of revolution. In the first case, the rectangle was touching the axis. In the other case, the rectangle was away from the axis, giving us, in the first case, a disk, in the second case, a washer. But in both cases, the rectangle was perpendicular to the axis of revolution. We can ask now, what if we have a rectangle that is parallel to the axis of revolution? What kind of solid will this generate? Well, let's see. Suppose first that we have a vertical axis of revolution, and about this axis we revolve a small rectangle, but now that is away and parallel to the axis of revolution. What kind of solid will this generate? And again, we imagine this being an infinitesimal rectangle, so where the width is shrinking to 0, so you can almost think of this rectangle being a piece of string. And now you revolve this rectangle about the axis, and if you can imagine revolving very rapidly, it will trace essentially a shell. Think of an aluminum can where the top and the bottom is missing. So all you have is the body of the can, not the top nor the bottom. So let me try and draw this. So you can see this is your rectangle. Now again, the center of your solid is given by the axis of revolution, so the axis goes right through the center of the solid, and you really see you have essentially just an aluminum can, because again we think of this being an infinitesimal rectangle, so the width is approaching 0. And as you revolve the rectangle about the axis, it really gives you the outside body of an aluminum can, but there's no top, there's no bottom. Okay, so now we ask, what is the volume of this shell? This is called a cylindrical shell, or simply a shell. Well, this seems more complicated than just a disk or washer. But we can at least find the basic measurements, right? We have, if you look here, the radius of this shell, there's the height of the shell, and there's the thickness of the body of the shell. So clearly, the height of the shell is the height of our rectangle. Since we have a vertical rectangle, the width is a small change along the x-axis. Since we want an infinitesimal rectangle, this is denoted by dx. So the width, the thickness of the body of our shell is dx. Now, there is also the radius of the shell, going from the rectangle to the center of the shell. And if you think of it, well, if you go back to here, we are going from the center of the shell to the rectangle, but the center of the shell is the axis of revolution up to the rectangle, so this is right here the radius of our shell. We can call this uppercase R. So now we have our measurements. We have the radius of the shell, the height of the shell, and the thickness of the body of our shell. But how does that help us find the volume of this cylindrical shell? The idea is very simple but very clever at the same time. Imagine yourself with a good pair of scissors, and you could cut through this shell, just one side, cut it open. If you cut this open, then you can flatten it out, just press on it until it becomes flat, and what happens is it becomes a rectangle. And again, imagine yourself with a good pair of scissors, cut through one side of the shell. Now the shell is open, and if you flatten it out, you press on top of it, both sides will unfold, and when it's fully pressed down against the surface, it will just become a rectangle. And now the volume will be very easy to figure out. So you say, well, okay, what is the thickness of my rectangle? That is, of course, the thickness of the shell, given by dx. The height of the rectangle, of course, is the height of the body of the shell, h. All we're missing now is the length of the rectangle, but if you think of it, the length of the rectangle is the circumference of the shell. But the shell is simply a circle, and so the circumference is 2 pi r. And so the length of the rectangle being the circumference of the shell is 2 pi r. And now the volume of this shell is quite trivial once it's viewed as a rectangle. The volume is the base, 2 pi r, times the height, h. This gives you the area of the rectangle times the thickness, dx, gives the volume. And that's it. So if you have a vertical rectangle that is parallel to but away from the axis of revolution, as you revolve the rectangle about this axis, it generates a shell. Think of it as an aluminum can with no top and no bottom. You need the radius of the shell, the height, and the thickness, dx. And think of cutting the can open, the shell open, and flatten it out on a surface. Then it becomes a simple rectangle, the height being the height of the rectangle, the thickness being the thickness of the can, and the length is of course the circumference given by 2 pi times the radius. And the volume is 2 pi r times h, surface area of the rectangle, times the thickness dx, and that's it. Of course, you have the exact same result if the axis and the rectangle, were both horizontal. So you can imagine now having a horizontal axis of revolution and having a rectangle that is also horizontal, therefore parallel and away from the axis. As you revolve this rectangle about the axis, you will get a shell, but instead of being upright, it will be, of course, standing on its side. You'll need, as before, oh, I'm sorry, I meant to include here that this was the radius of the shell. As before, everything stays the same except for one difference, being the width of the rectangle. You need the height of the rectangle. This will be the radius of your cylindrical shell. And now the thickness, the width of the rectangle, is no longer a small change in the x-axis, but a small change along the y-axis, therefore they're given by dy. So you can now draw your cylindrical shell on its side. And the idea is the same, right? We have the thickness of the body of our shell, and as before, the center of the shell is the axis of revolution. And we need, of course, the thickness of the body of our shell, given by dy. We need the height of our body. That's just the height of the rectangle, clearly. And finally, we need the radius of our shell being the distance from the center to the rectangle. And really think of here that there are no two radii. There's no shorter radius, and longer radius, because what we have is an infinitesimal rectangle. So the width here, dy, is representing a width shrinking to 0. So you can really imagine the rectangle having a 0 width, so essentially just being a piece of string. So this right here is an infinitesimal width, so it really is kind of just one outer rim. Really think about an aluminum can. You really think of the thickness being just one little of the same thing. And of course we go from the axis of revolution, the center, to the rectangle, and that is the radius. And the argument is the same as previously. If you cut your can open, it becomes a rectangle. The measurements are all the same. The radius doesn't change, the height is still the same. The only difference is instead of a thickness given by dx, the thickness is given by dy. So our volume is essentially unchanged. So always think of it as cutting this shell open and flattening out. So we get the length, the circumference, 2 pi r, times the height, h, gives you the area of the rectangle. And all you're missing is the thickness, and in this case it's given by dy. And that's it. So if you ever have a rectangle that is parallel to the axis of revolution and away from it, as you revolve the rectangle by the axis, it generates a cylindrical shell, or simply a shell. You need the radius of the shell, the height, and the thickness being the width of the rectangle, whether it is dx or dy. And the volume is very simply obtained. If you think of cutting one side of your shell open and flattening it out, you have a rectangle. The length is the circumference of the shell, 2 pi r. The height is the height of the rectangle, h. And the thickness is either dx in the case of a vertical rectangle, or dy in the case of a horizontal rectangle. And that's it. So with those three cases, with a disk, a washer, and a shell, we can now find the volume of solids of revolution that are much more complex than simple rectangular regions.